are back again. We are going to be doing another video lesson as we continue not to be able to get together. So this is Physical Science, Module 14, Waves and Sound, the second half of the chapter. So it's part 2. We're going to start with a short review. In this chapter, we were talking about waves because sound is a wave. We started by examining the transverse wave, which is the wave that we're most familiar with because we see them all around us. A transverse wave is a wave where the disturbance that makes up the wave is moving perpendicular to the direction in which the wave is traveling. And as you look at the diagram there, you see that the wave is oscillating or vibrating up and down, and there's the up and down arrow by the woman's hands, and the wave is vibrating up and down, and it is perpendicular to the wave as it goes out from the woman. Remember that perpendicular means that the lines come together at right angles. The highest point of the wave is called the crest. The lowest point of the wave is called the trough. And we can measure the wavelength by either measuring from crest to crest or from trough to trough. Remember that we're going to be using the Greek letter lambda to designate wavelength when we are doing math in this chapter. Cutting the waves in half, with just the crests on top and just the troughs on the bottom, we can measure the amplitude of the wave. That's the height of the wave, just the height of the crest or the depth of the trough. And when we do the math problems, we're going to use the capital letter A to designate amplitude. Remember also that we are going to be talking about the frequency of a wave. Remember that the frequency is how many times the wave hits a certain point every second. Longitudinal waves we're a bit less familiar with just because we normally don't see them. Remember that sound is a longitudinal wave. Longitudinal waves are waves where the disturbance that makes up the wave is moving parallel to the direction in which the wave is traveling. Remember that instead of having crests and troughs, in a longitudinal wave we have compressions and rarefactions. Compressions are where the wave has compressed into a smaller space, and rarefactions are where the wave has expanded into a larger space. Just like with transverse waves, we can measure the wavelength of a longitudinal wave. Remember that in this case, we're going to be measuring from the center of one compression to the center of another compression, or from the center of one rarefaction to the center of another rarefaction. And once again, we're using the Greek letter lambda to designate wavelength in our math formulas. We are also able to measure the amplitude of the wave, and so we cut the wave in half, and we measure the height of the wave. That is the amplitude. And when we use amplitude in math formulas or equations, we are going to be using the capital letter A to stand for amplitude. Remember that we can also measure the frequency of a longitudinal wave. The speed at which sound travels from one place to another depends upon the medium and how closely packed the molecules are in the matter. A medium is a substance that allows sound waves to travel through it. Where there is no medium, no sound can be transmitted. Of the three mediums, solid, liquid, and gas, sound waves travel the slowest through the gases, faster through liquids, and fastest through solids. And we went over this last week, so this is just a review of that. On your own question 14.5 asked, remember from Module 9 that the outer core of the Earth is liquid, but the inner core is solid. If a geophysicist is studying how sound waves travel through the core, would he expect the sound waves to travel faster in the inner core or the outer core? Remember that sound waves need a substance to travel through, and they travel by vibrating the particles. So we have a picture here of the solid, the liquid, and the gas. The particles in a solid are closer together than in a liquid or a gas. So this means the vibrations are more easily passed from particle to particle. So sound travels faster in a solid. So since the inner core is a solid and the outer core is liquid, at least according to current theories, the sound is going to travel faster in the inner core. Last week, we also discussed supersonic speed, any speed that is faster than the speed of sound in the substance of interest. And we also discussed what a sonic boom was. It's the sound that's produced as a result of an object traveling at or above Mach 1, where Mach 1 is the speed of sound. Remember I said that for the quiz last week that we were only going to need to remember the definitions, and that this week we would go over Mach 1 a little bit more. That's what we're going to do. On your own question 14.6 said, a jet is traveling at Mach 1.8 when the temperature of the surrounding air is 0 degrees Celsius. What is the speed in meters per second? Remember that we have a speed equation which says speed equals 331.5 plus 0.6 times the temperature, and then we label it meters per second. Remember that the V there stands for speed and the capital T there stands for temperature, but not temperature in Fahrenheit, temperature in centigrade or Celsius. So we're going to go ahead and plug in our numbers. We know that the temperature is 0 degrees Celsius, so we plug that in. And remember that because of order of operations, we're going to do the multiplication before we do the addition in that equation. So 0.6 times 0 is going to equal 0. So very easily we find that the speed is 331.5 meters per second. Now, that's how fast sound can travel at that temperature. But then when we go back to the on your own question, it says that a jet is traveling at Mach 1.8, and that is the speed that Dr. Wall is asking you to find. So we're going to have to figure out what Mach 1.8 is. And we do that very easily by multiplying 1.8 times the speed of sound at that temperature, 331.5 meters per second. And when we do that very simple multiplication, we find that the answer is 596.7 meters per second. I thought it might be a good idea to do a couple more of the mock math problems since they do turn up on the test. So here's a second one, and I'll walk you through it again. A jet is traveling at Mach 2 when the temperature of the surrounding air is 10 degrees Celsius. What is the speed in meters per second? So once again, we're going to use our speed equation. We get 331.5 plus 0.6 times the temperature in Celsius, and we're going to label it meters per second. We plug in 10 degrees, and we do the multiplication. 0.6 times 10 equals 6, and very easy to add that to 331.5, and we get the speed of sound at this temperature as being 337.5 meters per second. Now we need to figure out what the speed of the jet is that's traveling at Mach 2. So we're just going to simply multiply 2 times 337.5 meters per second, and we get the answer 675 meters per second. One more of these problems. A jet is traveling at Mach 1.5 when the temperature of the surrounding air is 22 degrees Celsius. What is its speed in meters per second? I'm going to use the speed equation again, 331.5 plus 0.6 times the temperature in Celsius. Label it meters per second. We plug in 22 degrees Celsius, and we're going to do the multiplication first. 0.6 times 22, we get 13.2 as the answer there. We're going to add that to 331.5, and we discover that the speed of sound at 22 degrees Celsius is 344.7 meters per second. Now we need to find out how fast the jet that is traveling at Mach 1.5 is going. So we're going to do that by multiplying 1.5 times 344.7 meters per second, and the answer is 517.05 meters per second. Now, a lot of the chapter has been setting the groundwork for sound. We've discussed the different kind of waves. We've talked about the different parts of the wave, the amplitude of a wave, the frequency of a wave, the wavelength of a wave, the medium through which waves travel and how they travel faster through solids than they do through liquids, faster through liquids than they do through gases, and why that is. Now we're going to get into some practical application in the second half of the chapter. So the first thing that we get to is the fact that the wavelength of sound has a dramatic effect on how we hear sound. And we have several experiments that Dr. Weil walks you through. And if I have the time, I'll go ahead and film us doing some of those experiments. But I encourage you to do as many of those experiments as you can at home on your own. So, wavelength leads to frequency, which leads to pitch. We can measure the wavelength of a wave from crest to crest or from trough to trough. And we note that different waves have different wavelengths. And because different waves have different wavelengths, they also have different frequencies. Remember that a frequency is how many times the wave hits a certain point every second. And just looking at the two waves on this slide, you can see that the bottom wave is going to hit more times per second than the top wave. So it is going to have a higher frequency, and the wave on top is going to have a lower frequency. Now, pitch, remember, is an indication of how high or low a sound is. That's how we interpret the sound. And how high or low we interpret the sound, our ears interpret the sound, is primarily determined by the frequency of the sound. Sound waves with low frequencies have a low pitch to us. And so when we hear very low musical instruments, for example, they have a picture here of either a bass violin or a cello, and they have very low sounds. They have a low frequency, a low pitch. Meanwhile, sound waves with a high frequency, our brains interpret them as having a very high pitch. And so instruments like violins and violas have very high frequencies and thus have very high pitches. Now, one of the experiments that we would have done together in class was the experiment where you fill a bottle up with water. And like I said, if I have the time, I'll go ahead and film us actually doing that experiment. But if you are able to do that at home, please do that at home and see it for yourself, hear it for yourself. So in that experiment, Dr. Weil explained, and I'll review it now, that when there was very little water in the bottle, that the sound waves had a far distance to go, and so they had a very low frequency because they had further to travel up and down the bottle. Meanwhile, when there was a lot of water in the bottle, the sound waves had a very short distance to travel, and so they could do that a lot quicker, and it had a very high frequency. And so things that have a low frequency have a low, deep sound, and sound waves that have a high frequency have a high, piercing almost sound. Remember, just by way of review, that we can determine the frequency of a sound wave by using this particular equation. Remember that the F in this equation stands for frequency, the V in this equation stands for speed, and the Greek letter lambda stands for wavelength. On your own question, 14.7 says, many flautists also play the piccolo, an instrument that looks like a very small, short flute. Which instrument, the flute or the piccolo, can produce notes with the highest pitch? And so I thought it might be helpful just to look at a picture of a flute versus a picture of a piccolo. And notice the flute is much longer than the piccolo. And so going back to our experiment, remember with the bottle, when the sound waves had a long distance to travel, that it had a lower frequency, and so it had a deeper sound. Meanwhile, when the bottle had more water in it, the sound waves had a shorter distance to travel, had a higher frequency, and so had a higher pitched sound. So just looking at the two, logically you can tell that the flute is longer, the wavelengths are going to be longer, and so it's going to have a deeper sound than the higher pitched piccolo, where the sound has a shorter distance to travel, has a higher frequency, and a higher sound. At this point, Dr. Weil also had a discussion about sound that we can hear versus sound that we cannot hear. The area of audible sound goes from about 16 hertz to about 20,000 hertz. So we can hear a lot, actually. There's a lot that humans can hear. The sound that we are able to hear is called sonic sound. Sonic means we can hear it. Sound below 16 hertz is called infrasound. And it's interesting because for years we didn't know about the existence of infrasound, but scientists studying elephants were intrigued with the way that elephants were able to communicate, and they thought at the time that they were communicating without sound. When they had more sophisticated ways to record rumblings of elephants, they discovered that they were actually rumbling to each other or communicating to each other in sound below 16 hertz in frequency. And so humans, under natural conditions, cannot hear that. But with special recording instruments, we can pick that up and study it. They also more recently discovered that cats also communicate with each other using infrasound. On the other end, there are frequencies that are higher than 20,000 hertz, and we call that ultrasound. We know that bats use ultrasound in order to send out signals that bounce back to them when they are using their echolocation. On your own question, 14.8 said, are the wavelengths of ultrasonic waves shorter or longer than the wavelengths of sonic waves? So ultra means beyond. It's beyond what we can hear. And with the diagram here in front of us, it's easy to see that the wavelengths of ultrasonic waves are far shorter than the wavelengths of sonic waves. But in order to answer a question like that on the test, you're probably not going to have a diagram. You're perfectly within your rights to draw a diagram if you want to, and you can make something like this, labeling the longer frequencies infrasound, the medium frequencies sonic, and then the shorter frequencies ultrasonic if you want to. But you may just want to remember that ultrasonic is beyond what we can hear. And so their wavelengths are very short, very short. And so they have very high pitch beyond what we can. Dr. Wall also had a discussion of the Doppler effect. And as you look at this diagram here, you'll see that static sound has a wavelength as it goes out from the source of the sound that is very even. But when something is moving, say for example you are moving, you are walking, or a car, in a more extreme example, is moving, notice that in front of the movement that the sound waves begin to bunch up, and behind the movement the sound waves begin to spread out. And so scientists call that the Doppler effect. And the definition of the Doppler effect is right there: an increase or a decrease in the frequency of sound, light, or some other wave as the source and the observer move toward or away from each other. The effect causes the sudden change in pitch, noticeable in a passing siren. And there was an experiment in the book just to hear that. Rather than do that, I might just go online and find a video where somebody else has already demonstrated the Doppler effect and add that link to your resources this week. All right, back to the practical applications. We've already discussed the wavelength of sound has a dramatic effect on how we hear the sound. If we have very long wavelengths, the frequency is lower and the pitch that we hear is lower. Meanwhile, if the frequency is higher, the wavelength is shorter, and what we hear is a higher pitch. In addition to that, the amplitude of a wave governs how loud the sound is, and Dr. Weil discussed that in the book. And so we have a diagram here of common indoor and outdoor noise levels. Remember that we measure noise levels in what's called the Bell scale. And a decibel has the prefix deci in there, which means 10. So for every 10 decibels, we have 1 bell. For every 10 decibels, we have 1 bell. Remember also that each step up on the Bell scale is an increase in the intensity of the wave by a factor of 10. Not by a factor of 1, but by a factor of 10. So every time you go up 1 step on the Bell scale, you have to multiply. Remember, the word factor is always a clue. That means you have to multiply. And what are you multiplying by? You are multiplying by 10. And so we have an example here. The sound from a typical vacuum cleaner is about 60 decibels, while the sound of a rifle firing is about 140 decibels. How many times larger is the intensity of the waves coming from the rifle as compared to those coming from the vacuum cleaner? And so the first thing in answering questions like this is that we need to convert decibels back to bells so that we can count how many steps up on the Bell scale the two different sounds, the difference between them on the Bell scale. So to convert 60 decibels, we just divide by 10 and we get 10 bells. And to convert 140 decibels, we just divide by 10 and we get 14 bells. So the difference between 6 bells and 14 bells is 8. So we've gone 8 steps up the Bell scale. So we have to multiply by a factor of 10 8 times. 1, 2, 3, 4, 5, 6, 7, 8. And when we do that, we end up with 100 million times larger. Pretty intense. On Your Own question 14.10 says the sound from a typical power saw has a loudness of 110 decibels. How many times larger is the intensity of the sound waves from a power saw as compared to those of a normal conversation, which come in at 40 decibels? So remember, the first step is to change decibels to bells so that we can find the difference on the Bell scale between the two sounds. So 110 decibels when we divide by 10 gives us 11 bells. 40 decibels when we divide by 10 gives us 4 bells. The difference between them is 7, and so we have to multiply by a factor of 10 7 times. 1, 2, 3, 4, 5, 6, 7 times. And we end up with 10,000 times larger. And we got the answer right. There's that wonderful green check mark. All right, back to practical application. We have one more practical application. We've talked about the wavelength of sound having a dramatic effect on how we hear the sound. We've also talked about the amplitude of sound governing the loudness of the sound. And the last practical part of this particular chapter is a discussion of how we actually use sound waves in our everyday lives. So I have a diagram here of some of the ways that we use sound waves. For example, in the medical field, we use ultrasound to get images inside the body. If you have injured your knee, for example, they might do an ultrasound on your knee to see the image. Basically, an ultrasound directs ultrasonic waves into your body, and as they bounce out, they give the special instruments an image of what is going on inside your body. This is seen as being less harmful than taking an x-ray, because as you know, x-rays can be harmful to people, especially if that you have an x-ray too often, that x-rays actually kill the cells in your body. So ultrasound is a good alternative to that. We also use sound waves in communication through telephones and through radios. We use sonar to navigate, and then they also have some examples of using sound waves in nature. Bats, porpoises, whales, and other animals use echolocation. And of course, we use sound all the time to make music. It's kind of fun, a fun use of sound waves. All right, this next section is going to be a review. Remember I said earlier that we were going to review how to calculate frequency. I have a question here. What is the frequency of a wave that travels at a speed of 60 meters per second and has a wavelength of 0.3 meters? Remember that we're going to use the frequency equation, where F equals V over lambda, or frequency equals speed divided by wavelength. And so this is a simple equation to use. We simply plug in the information we have. For the speed, we have 60 meters per second. For the wavelength, we have 0.3 meters. And when we do our division there, 60 divided by 0.3 equals 200. And remember that we have to label it, and scientists have come up with the handy dandy label hertz, and so we are just going to use hertz. Remember that hertz is the unit used to measure the frequency of vibrations in waves, and so we label the answer hertz. Here's another one. What is the frequency of a wave that travels at a speed of 75 meters per second and has a wavelength of 0.5 meters? Once again, we'll use the frequency equation. And we have frequency equals 75 meters per second divided by 0.5 meters. And when we do the math, we get 150 hertz. During a thunderstorm, the temperature is 12 degrees Celsius. If you see a lightning flash and hear the thunder 4 seconds later, how far away did the lightning actually strike? This is going to be a speed problem. Remember that I said that since we're not together, I'm giving you a break, and I'm always going to give you the speed equation. So we're going to be using the speed equation to calculate this, where speed equals 331.5 plus 0.6 times the temperature in Celsius, and we'll label it meters per second. So we plug in the information, and then we're going to multiply first because of order of operations. 0.6 times 12 degrees equals 7.2, and then we're going to come back and add that to 331.5, and the final answer is 338.7 meters per second. Remember that in this kind of problem, however, that what they really want is the distance. You hear the thunder 4 seconds later. How far away did the lightning actually strike? And so this is one of those two-part problems. So in order to find the distance, we're going to use our handy-dandy speed equation that we memorized earlier in the year. And if we forget what the speed equation is, all we have to do is remember miles per hour. Which gives us a distance traveled over a time traveled. And that's exactly what the speed equation is. Speed equals distance traveled divided by time traveled. We'll go ahead and plug in the numbers we already know. We know the speed, 338.7 meters per second. What we don't know is the distance, but we've been given 4 seconds, so we go ahead and plug that in. Remember that we're going to multiply both sides by the reciprocal of 1 over 4 seconds. And so basically what we're doing is multiplying each side by 4 seconds. That is going to cancel out 4 seconds on this side, and on leaving distance by itself, we've isolated distance. And remember, in algebra, whatever you do to one side of the equation, you have to do to the other side of the equation. So we're multiplying 338.7 meters per second by 4 seconds. I remembered this time to go ahead and cancel out the seconds. And when we multiply 338.7 meters times 4, we get the answer 1,354.8 meters. That's how far away the lightning strike was. And that is all we have for today.